before. So I found some lecture notes from...
So next we have Tom Hall, who's very kindly interrupted his international trip to take in the sights of Milton Keynes and join us here. I was thinking of a word to describe Tom. He's a mathematician, computer scientist, physicist, mountaineer, reformed arsonist. Is it safe to open it up to the audience?
I wish I hadn't told you that yesterday.
Me,
I'm not reformed, it's a lie.
Those of you know him are welcome to contribute. I think the best word is explorer. We've had lots of tales of exploration this conference. We've had Carsten's exploration into computational geometry, into Håkon and his explorations into assembler, Portia and Chris. And this is another real tale of exploration into the search of universality. So can you give a round of applause to Tom Hall?
Thanks, Malcolm, for that terse and begrudging introduction. No, that was very wonderful, thank you. So I'm Tom Hall. You might know me as that Tommy Hall on the internet, or as a sort of incredibly well-dressed gent about town. So I'm going to talk today about an idea that sort of appeared on my radar again when reading Dan Dennett's latest book, which is great. It's called Intuition, Pompton, Other Tools for Thinking. So Dan Dennett is a contemporary philosopher, and he has a section in this book which is got lots of other interesting stuff in, but the chapter is called The 7 Secrets of Computing Power Revealed. So it's a book for what I like to call as the enthusiastic non-specialist. So it's for people not necessarily steeped in programming language theory or in computational theory, but they're smart and they're willing to make efforts. And interestingly, he does actually introduce this idea, which I'm going to do in a moment, which is the unlimited register machine. He has people simulate them and build an intuition for them, and then the idea is, in order to understand computation, to demystify what computers do as their sort of new idea, sort of on the order of the printing press or mathematical notation or whatever, and laymen, or let's say the enthusiastic non-specialists, should have like an understanding of how they work. So the formalism is called unlimited register machines. Well, it's really weird hearing cars whizzing past. So the concept, so we sort of do the definitional thing. So a register is just a location to store a natural number. So every register holds a number. It's unlimited in the sense that you can have as many of them as you like, but there's a finite number for any particular program. And they can hold a number of arbitrary size, again, but finite. So arbitrarily big, but finite. And a program is a finite sequence of instructions. Again, one could imagine an infinite list of instructions that you executed in order. But the program is actually a finite sequence of instructions. Our particular unlimited register machine we're going to look at is a free instruction machine. So the free instructions are, I'm just realizing I was going to give myself some kind of time. I don't know, maybe I should. That's at least where we were, I think. So yeah, there's three instructions. End, which is halt, you're done computing. Increment instruction, increment a register. So this says increment register n, and then move to line m of your program. So every instruction other than the halt instruction is actually a go-to. So we're going to jump around our programs, and the only branching condition is involved in the next instruction. So you read this as deb, decrement and branch, deb. So it's decrement register n, go to line m if you successfully decrement it. If you can't decrement it, if it's already 0, go to line p instead. So the only branching condition is when you try and decrement a register that's already 0. Is that so far so clear, yeah? Cool. So a state then is you at a particular execution of a program, you're on a particular line. You start at the first line, line 0. You jump to some other instruction. So every time you execute an increment or a decrement instruction, you jump to another line in the program until you get to a line that says halt. Now, or end. You execute the end instruction. If you try and jump to a position in the program that doesn't exist, that's just deemed to be an end. So you've jumped somewhere that doesn't exist. That's kind of an invalid program, but we just say that you halted. So computation is a sequence of states. And these things can perform computations, as we'll see. So our first program looks like this, indexed 0 to 4, so it's a five-line program. And we say we decrement and branch register 1, then go to line 1. Otherwise, we go to line 2. And then the first instruction is increment register 0, then go to line 0. So one way that you simulate these is by just writing out. We can see that I've put here register 0, register 1, and register 2. You can see from scanning down the first argument to our instructions that we only reference registers 0, 1, and 2. So I've just started off a line with register 0, 1, and 2. And L is the line that you're on. So the first time we start at line 0 in the program. That's by convention. Register 0 is initialized to 0. That's again a convention. We're going to store the answer to our program in register 0. So the end result of executing this register machine is whatever happens to be the value of register 0 when you halt. Okay? So our inputs are stored in the other two registers. So all of these functions are actually variadic. We can have the initial state of as many registers as we want. We can then perform the computation, and we take whatever is in register 0 is the result. So here, if we've initialized register 1, register 2 as 1 and 2, and we're on line 0. So line 0 says, decrement register 1 and go to line 1. So can we decrement register 1? We can. So register 1 becomes 0. Then we then move into line 1. And we keep register 2 and register 0, we just copy, we haven't changed them. So we do that every single instruction. We're now at instruction 1, which is going to be increment register 0, go back to instruction 0. So when we go back to instruction 0, and now at instruction 0, we've incremented register 0, and then we copy the other two registers. Is that clear? So every time we step through, and we sort of perform this, the computation ticks forward. Does anybody know what this is doing, by the way? Can anyone? It's an adder, yeah. So we decrement one register until we're done. And I've got a little simulator for it. So we initialize the registers. We tick around, jump in between instruction 0 and 1 until the first register is 0. So you can see this, we're decrementing register 2 right now. And as soon as that's 0, we jump somewhere else, and we keep decrementing register 1, and we're squirting the contents, the answer, into register 0. Does that all make sense? Cool. And so there you go, and it's about to hold. I used two big numbers. This is tedious, isn't it? Okay, done. There you go. So we've successfully performed addition. So another way of representing these is like a graphical representation. So the best way to go through these is to imagine you going through them. Think under what conditions you branch, because remember, you only branch when the register's 0. In this representation, the double arrows are your branch on 0 condition. The single arrow is your usual, the default one. So if you watch here, I've increased the size of my mouse, so hopefully you can see. We start off, if register 1 is 0, if we try and decrement it and it's already 0, we halt. Otherwise, we decrement register 1, go here, which decrements register 2, and then if you look, we're kind of stuck in this loop for a while until register 2 is 0. So if you imagine what's happening as we go around this loop, we're decrementing register 2, we're incrementing register 0 and register 3. So everything in register 2 gets copied to both register 0 and register 3. And then when register 2 is empty, there's a copy of it in register 3, there's a copy of it in register 0, which is where our answer is going to be. And then we go down here, and then we keep decrementing register 3, and then increment in register 2, so we're actually copying back register 2. So a copy of register 2 goes into register 0 and register 3, and then gets copied back to register 2. So we're actually, and how many times do we do that? We do that as many times as we have something in register 1. So for everything in register 1, we put a copy of register 2 in register 0. Does that make sense? So what is that? What's the computation that's performing? Multiplication is exactly right. So if you don't get it straight away, that's fine. So I should have given like a sort of caveat at the beginning. The best way to generate an intuition for these is to calculate them, perform them by hand, build your own, etc. So we're going to like skip all of that intuition forming stuff that might have happened if you, for instance, read a book or did a sort of semester course at university or whatever. So we're going to try and condense like a semester of university into like 20 minutes. So yeah, my expectation isn't that everybody gets everything, but rather that people are intrigued. So building a DSL, this is a closure conference, but the actual code is fairly trivial. So I have a function called evaluate URM, which takes as arguments a URM program. Interestingly, this just returns data, so I just made it look like closure, but really that's just it just returns a vector with a symbol deb and then the instructions. So it's just really data that represents the program. And then I can say things like, I can expect 3 to be the result of calling add with 1 and 2, so all sort of fairly mundane. So the state, as I said before, is a position, a collection of registers, and the program, and we update the state with every instruction, and we jump around the program till we halt. Like all sort of interpreters, it's basically a condition statement. It switches on what type of instruction you told it to do, and it kind of appropriately updates the registers. I won't spend a long time talking about the closure code, even though this is a closure conference. And then here's the sort of 7 secrets of computing power as from Dan Dennett. So they kind of it's fairly mundane until about secret 4. So he says, since a number can stand for anything, it can stand for an instruction or address. So if we've said that numbers can stand for anything, we can represent some idea as a number, perform a computation on it, but then like we project an interpretation onto it, like with our own programs. So all programs can be given a number. So in the book, this is kind of like the end of the section. Is like, since all programs can be given a number, you could make a machine that took as input a number that represented a program, execute the program that it describes, and isn't that amazing? He says basically that's what a computer is. This idea of like Church-Turing equivalence is like that any improvements, any faster computers or all that, they're doing exactly the same sort of thing. And they're equivalently powerful. Anything is just really a speed up. So this formalism is somehow like maximally powerful. But he kind of leaves it. He doesn't give a concrete implementation of the universal machine. So that's kind of what I was then looking around for. So I found some lecture notes from Andrew Pitts at Cambridge, where he actually had a concrete implementation. Or rather, he had a sort of description of a universal machine that happened to use the same free instruction register machine that Dennett used. So in order to do this, we need to use an idea that Kurt Gödel came up with for his incompleteness theorems. So you may or may not know, but one of the key moves in the incompleteness theorem is that the system permits an arithmetic, and then he has a way of expressing things as numbers, so using facts about arithmetic to kind of force this incompleteness result. Weaker systems can actually be consistent and complete, but that's kind of perhaps by the by. So this idea of Gödelization, representing things as numbers, is we're going to use because our inputs and the only thing our machines operate is numbers. But remember that the goal is we want to take a representation of a program, represent it as number, feed it in as an input to a universal machine, which will then execute that program as described on the input registers, which again are going to be expressed as a single number. So we need a way of expressing programs as numbers and lists of numbers as numbers. Does that make sense? So the goal for the next few slides is to try and get a way of representing lists of numbers as numbers, a way of representing instructions as numbers, and then a program is then a sequence of instructions, so therefore it's a sequence of numbers, which we can also represent as numbers. Is that clear? I think so. So thank you for all your very strong assertion that I was very clear then. Thank you. So we're going to build lists of things by building pairs. So it's a closure conference, so there's kind of less gap to join here. So once you've got pairs, you can get lists by doing this sort of linked list idea. So first we need a way of representing pairs of numbers as numbers. And the trick is, it uses like a binary encoding trick. So to represent the number, to represent the pair, 2, 3, I don't know if you know in Clojure, I didn't until I did this project, there's a way of expressing binary numbers. So if you say 2R, then you're in base 2, and you can say 1, 1, which is the number 3. So you can use binaries, and you could say, for instance, like 1, 0, and that would then be 2. So the binary code you can do. And we're saying this pair, 2, 3, so 2 on the left, 3 on the right. And if you look what we've got here, on the left of our binary expansion, these vertical lines are just for our understanding. So this is actually 5-digit binary number. On the left-hand side, we have the binary thing of the thing on the right of the list. And on the right-hand side, we have as many zeros as the thing on the left. So there's 2 zeros on the right, there's then a 1, and then there's a binary expansion of the thing on the right, on the left. I don't even know if that was correct, but let me show you an example. I realized it was correct, even if the video says otherwise. So we're trying to represent this 2, 3. So we say 2 has, or rather 3, has representation 1, 1, then a 0, sorry, then a 1. God, my brain. Every time I get up here, I promise I was drilling this at the back to try and make sure I didn't forget again, but I did. So here, this first bit is the binary representation of the 3, and then a 1, and then 2 zeros. So this is also the result of our code pair function, which I said it was 2, 3. And there you go. So I can successfully echo 28 in the REPL twice. Bravo. Oh shit, no, I wasn't begging for that. No, you're not supposed to clap at this point. There's a point later where you need to clap. So the number x, as many zeros as there is the x thing, then a 1, then the binary expansion of the y thing on the left, yeah? So that's how we're going to do it. What we're actually doing here is bitwise operations. So we're saying shift y across to the left, which is this way for you. So sending y this way, flipping a bit in that position, the x plus 1th position. So we're saying this is shifting y, x plus 1 position, x plus 1 places, then flipping the thing in the 2 to the x position. So we're flipping that, by adding 2 to the x, we're flipping that thing, so it's all zeros, then we flip that bit, and we've bit shifted y over. So that's what our function does. If you happen to, that's obviously just brackets in the equation if you know the mathematics. So we can code a pair with this. So my prosaic description may or may not have worked. My hope is that if you know Clojure, that this completely describes the strategy. So 2 to the power of x, and then times it by 2y plus 1. So we've got the same idea. Interestingly, so there's kind of this idea from SICP or similar things where this code is a method of expressing the idea. So I waffled a bit and I waved my hands and then I drew some mathematics or whatever. But actually now I'm giving you an executable spec that in particular goes both ways. So I've got a way to decode it and a way to code it. And actually you can be fairly convinced they're right, because I could write a test that asserted that they round-tripped, maybe even do some generative testing, and we could be pretty sure that this correctly describes the idea. So once we've got pairs, we can get lists using the idea of similar to lists. So we code a list by saying we're going to use Clojure destructuring, and I'm glad it's a Clojure conference. So we pick out the head and the tail, and we say if it's empty, represented as 0. So our null or empty list is represented by the number 0. Otherwise, we code the pair with the head as the thing on the left, and and you recurse, and you want the number that represents the rest of the list. And then you define that recursively. I should have mentioned before, our code pair function actually excludes 0, doesn't it? Because if we take x and y, we always add 1. So if you notice, that function actually excludes 0. That's important, because we're using 0 here as our null terminator, our sort of special case for building the lists. So to decode it is quite interesting. You take a number that's supposed to represent a list, you decode it using this function, which is the opposite of the function just given before, and then you say, well, if it's 0, then it's the empty list. That's our special case. Otherwise, unpick it, You then get a pair. You're using the decode pair function. The left thing is the head of your list. The right thing is the rest of the list, and you can recurse on it. If that's not 0, if that's not the null terminator, unpick that one, and then you've got 3 elements. If that's not 0 yet, unpick that one, and you then got 4 elements. So you can go through recursively and turn a number into, indeed, a list of numbers. So is that clear? That's a little bit complicated. But so our strategy is, we've got a way of taking pairs of numbers and getting numbers, and we've got a way of taking numbers and getting pairs of numbers. And besides the fact that we've excluded 0, every other number is in fact represented there. So demo lists. What this actually winds up doing, which is perhaps even more interesting. So if I say code list of 1, 2, 3, there's a kind of a different explanation, which is like a binary expansion again. So if I say 2R, and I think it goes 1, 2, 3, 1, 1, 2, 1, 0, yeah. So we were actually packing them, and we're saying, go in the opposite direction now, which becomes clear why later. So there's 0, so there's 1, 0, then there's a 1, then there's 2 zeros, which represents the 2, and then there's a 1, and then there's 3 zeros, and then you always terminate on a 1. So there's a way of getting, you can now see, between lists of numbers and all numbers. So we can represent lists of numbers. We can represent programs then. I might have to go faster. We can then represent programs. If we can code instructions, then programs are lists of instructions. So if we can successfully code instructions as numbers, then programs can be coded as numbers because programs are lists of instructions. And so we just need to find a way of coding instructions. Now there's 3 instructions, and so we're going to have to use a little bit of a trick. We can code a pair of numbers. So if you look what we're doing here, we're using an arity trick. So we're saying we're going to double the first number in the case of an int, and we're going to double the first number and add 1 in the case of a deb instruction. So all the deb instructions, the left number is an odd number, and all the int instructions, the left number is an even number. So when we decode those, the arity of the left thing tells us what kind of thing it is. We then know that, okay, well, if it's even, then that's an int instruction, so you've just got the pair of numbers that are needed. If you decode the pair and it's odd, then the other thing is actually not a single number, but rather the number that represents a pair, so then you can unpick that as well. And we use 0 again as our special case. So 0 is codes the end instruction because our code pair function, remember, excludes 0. So we can do the same trick again and use 0 as a special case. So in case you didn't know what so so the sort of hawk-eyed among you might have noticed that this is code pair star as the second function. So that actually is just a version of code pair that doesn't exclude 0. So it literally is just the decrement of code pair. So code pair was 1 to infinity, not including infinity. And then otherwise we either add 1 to it and then decode, or we code it and then decrement it. So is that clear? We've finessed it a little bit. And I think the reason that this is done, I've ran the machine without this extra instruction, and I think it's only there to create a proper bijection between numbers and programs. So it's worth thinking, if I did code pair here and not code pair star, what numbers wouldn't be then represented as programs? There's an interesting question here, and does the machine require this? I'm not 100% sure. I suspect it doesn't. So we should sort of move on and try and elucidate the machine. So I think I just said this in words, but again, the idea I kind of like is if my words weren't sufficient or I wasn't efficient or correct at describing them, here is precisely a description of the procedure just outlined. And in particular, it goes, it says what I just said, which is if the code's 0, then return the end instruction. Otherwise, let y and z be the decode. If it's even, then it's an int instruction, but we need to half what we had for y. If it's odd, then we just destructure again. So we've got Y, sorry, we got JK, so that's our I, which was half of Y, the decrement, yeah? So if you didn't understand what I said then, but you do understand closure, there is another description of it. So code in a program is just code list of mapping code instruction across the list of instructions, which is a program. So we can, in fact, do that. So I'll just show you now. Maybe I'm jumping the gun a little. So can we code the program add? Yes, we can. It's this gigantic number. Can we code the list 037? We did it just before. It happens to be 4,113 in our normal decimal expansion. So we have a machine that will take those numbers as input and then perform the computation described by the instructions. So I'm going to do a little bit of wishful thinking at first. So in order to do this, I'm using this very similar idea to before. So the stacks are a really good idea. So if only we had a way of pushing things and popping things from a stack, yeah? Copying in registers is really useful. So I'm just going to add 3 instructions. Copy takes a register and copies it, but without destroying. So there's 2 versions of the register then, the same number. We can push things into a register. So a register contains a number that represents a list of things. You can do an operation that does the equivalent of our code list function with an extra thing on the head. So we're pushing something into the register. So we're basically adding something to the front of the list. So we're operating on the number, but what we get is the equivalent of adding something to the head of the list, which we can then pop off. And the pop instruction says, pop from this register, which is representing a list of things, put the first thing in this other register. So what's remaining in the register is the tail of the list of numbers that we had represented. And what is in the target register is the head. So we can take things out and we can put things in to the registers. If we can do that, then we can build a universal unlimited register machine. So this is a machine, remember, that takes as input a number that represents a program, takes as its second input a number that represents all of the registers that you're feeding into it, and it then is going to perform the calculation, or the computation, sorry. Wait, I guess it's equivalent. So it's actually this many instructions, I think 16, and there's a diagram of it to help us understand it. So I'm going to, again, it would be very unreasonable of me to say you should look at this for the 3 minutes that I've given you, and you should understand it immediately, because it took me like several hours of pondering and stepping through it. But what I think I can do, I can short-circuit some of the process for you, so I can describe the highlights of it. But please go away and look at it, because the wonderful aha moment of figuring out how this machine worked, it was one of, I'm not going to say the finest moments in my life. That would be, sorry, I don't want to say that, even though it's true. I want it to not be true. So we start off by copying the program into another register. Then we keep popping instructions for as many things as there is in the program counter. So we copy the program, pop, 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 pop. We get to the line we're interested in, and then the register we're popping to contains the instruction we're interested in, yeah? I wasn't sure if I would get the goose pimples that I experienced in Strangely, but I do seem to have them again. So this still has the ability to excite me, it seems. If you try, remember I said before, if you try and jump to an instruction that's not there, halt. So that's exactly what this top bit's doing. You pop instructions, as many as there is things in the program counter. If your program counter is higher than the number of things in your program, then what happens here? We halt, do you see? So that's already part of the execution of our machine is now explicated. So then we say, that's the instruction we're interested in, pop it. So there's now one thing left in there, and there's the thing we've popped out. And then what do we need to do? We need to discriminate based on the arity of that thing and decide whether it's an increment or a decrement instruction. And that's exactly what happens here. So if you look, we pop, we decrement C, and remember, we branch only when it's 0. So here, look, we keep pushing and popping, but we're discriminating based on the arity of C here. So we were in that point where we're trying to discriminate. Is it an increment or is it a decrement? If it's an increment, we go one way. If it's a decrement, we go the other. So that's this here. This n plus here is our code per star function. Remember, when you decode it, if it's a decrement instruction, you need to increment the register before you do the decode. But the decode is equivalent to our pop. So here we've said, this is the decrement branch. Or, sorry, this is the decrement and branch, the deb branch of this program. I think I said that correctly. And then, so we go here, we then have this thing of registers that we popped, which was actually, we keep popping the registers. So we've got now in there the register we were going to operate on. And we discriminated here whether it was an increment or a decrement. We then do it. We then reassemble all the registers and put them back in. Then we actually go back to the beginning again and we copy our program again and do the same thing again. So it's kind of this procedure of copying the program, popping it till you get the instruction you're interested in, discriminating whether it's increment or deb, while popping the register that you're interested in somewhere else, changing that register, bundling up all the registers again, putting it back in as input, and starting again while updating the program counter to be what you wanted it to be. So it's performing the work of executing the machine. So I think it's wonderful. No, this isn't the bit where you clap. I'll show you. I'll show you with the bit where you clap. So, as previously discussed, get ready. This is the gigantic number that represents the program add. This is a moderately big number that represents the list 0, which is the 0th register, 3 and 7. And can we actually evaluate the universal unlimited register machine, which looks like this? Can we evaluate it? And then 3 plus 7 is indeed 10. Now is the bit where, thank you. Thank you for clapping genuinely, and then I'm sorry to beg it so hard at the end. So in order to kind of finish up, we need to make those wishes come true. We've got a 6-instruction machine that can simulate the behavior of any 3-instruction machine, and that might not sound, that might not sound exciting enough for you. So I think I was a little over. If you'll permit me, maybe 3 mins from now. So making the wishes come true, copy instruction, dead simple. We're going to copy register R into register S. This first bit, keep decrement in S, just zeroes out the register. Then for everything in R, copy it into Z, an auxiliary register, and copy it into S. So Z and S now contains R, and R's empty. I should point with my big pointer. R is now empty. Then we need to restore R from Z and then exit. So copy's easy, right? Push, I'm going to do now, which is to add something to the front of the list. Remember our code per function performs this calculation? I'm going to show you now how this machine performs that calculation. So it's quite subtle and intriguing. So the first thing we do is increment register Z. The next thing we do is based on the contents of L. For everything in L, we put 2 copies into Z. Do you see? So we added 1 at the beginning. Then for everything in L, we added 2 copies. That's our 2y plus 1. So our 2y plus 1 is now the contents of register Z. We then copy it into L. So everything in Z gets decremented and L gets incremented. So L now contains 2y plus 1. Then for everything in X, we go back and do that again. So what does that mean? For every time there's an X, go back and double, or rather copy L into Z twice. So twice L is now in Z. We copy L back to Z. So for everything in X, we double the thing that's in L, which was this. So we've actually, this machine performs that computation. An exercise for the assiduous listener is how does pop work, and it's very similar. And again, if you can get this before you leave today, hopefully you'll get that goose pimply excite that seems to be induced in me by unlimited register machines. So yeah, have a look through it, figure out how this is performing pop, and then yeah, next steps, I would like to do a graphical editor and simulator. So I do actually have this thing, but it's kind of hard-coded at the moment, the program, whatever. I'd like people to be able to write their own programs, simulate them. I can't yet do the universal register machine in my sim because it uses JavaScript, and you saw the size of that number, so it's like, I actually took about an hour to port the closure one I had onto this, and I thought, great, I'll run the unlimited register machine, boom, and then the registers just went infinity, and it was infinity with a capital I, and I don't know where it comes from, whether it's React or JavaScript or whatever. It's like infinity with a capital I. I was like, no, that's not the point. So I haven't got that working yet. I would also, somewhere, yes, sorry. A faster interpreter for the free instruction URM. So we cheat and we use 6 instructions in order to generate the URM so that we can run it. It was originally a speed up why I added those free instructions, because if you try and execute the copy machine, it goes, well, we'll keep decrementing this girdle number and incrementing the other one because we need to copy the program, and then you're waiting for the heat def of the universe while one by one that giant number is incremented and decremented. But you could JIT it, you could detect you got into a loop, and you could say, well, let's just skip forward like 11 trillion billion, however many quadrillion steps, and we'll just declare this to be the state of the machine. It's crying out for property-based testing, so I've actually got a strong assertion that any number gives me a program, and any program gives me a number, and like vice versa. I could even feed it into the universal machine and assert that it's the same as running the program with the number, and so it's kind of crying out for that. If you want some more of the history of the idea of universality, this is an excellent book. Martin Davis actually is a kind of like logician himself, so he was a student of various of the key figures. Very nice treatment of Boole. Turns out he was a very nice chap. Leibniz was actually sort of forced to be a biographer, which is a real shame because he was a very good mathematician. So his kind of benefactors were like, write our family history, you. And he was like, oh, but I want to do some maths. A book that uses a slightly different URM formalism, but in much more rigorous mathematical detail, goes into what it means to compute as well worth looking at. Any questions? I've answered the first question I always get. Any questions, or shall we move on? Go on.
Can you use this to find examples of Gödel's incompleteness theorem, actual concrete examples?
It permits, and I think Malcolm put it in the abstract for the talk, but I can't get there in 30 minutes. This formalism permits a very good demonstration of the undecidability of the halting problem. I don't know what it would mean to exhibit an example of Gödel incompleteness in this formalism. I'm not sure I understand your question, so forgive me. Any other questions? Go on. I'm not going to do it extemporaneously. Does that mean made up on the spot? What do I mean? I'm not going to make it up on the spot or struggle to remember posh words in order to sound clever. Not much longer. I do intend to do a similar to Dennett treatment of build a few, build up an intuition, design a few yourself. Oh, by the way, I want to do one thing that's like there's an intermediate representation, it feels to me, between this graph representation where everything is a node. Oh, by the way, I have the 67 instruction. I know you want to say it. I have the 67 instruction universal machine with 3 instructions. Does that make sense? The 67 line, 3 instruction universal register machine, and I've written something using rhizome that will generate a graph of the program. But it's something like 67 instructions to have a 3 instruction only program for the universal unlimited register machine. And that is the graphical representation of it. There's some kind of intermediate representation between a list of instructions and the graph. So it has like somehow a clumpiness, like these 3 instructions always follow one another, and then we go somewhere else, and then these 3 follow another. So a scratch-like thing where you can design these with, drawing lines and stuff, I think would be awesome. So I don't think, I'm already over time. Why am I even taking more questions? Thank you very much for your indulgence. It's been a pleasure to be up here. Thank you.